Hello, everybody. Now is our time to start talking about something kind of different, kind of new, and that is statistical mechanics. So, we've spent the semester so far talking about quantum mechanics, and this is focused on small things, and this is appropriate for chemists to care about because we care about small things, atoms and molecules, most of the time. But statistical mechanics will be our bridge to what you talked about in Chem 317 if you took it, and that's thermodynamics, and also classical mechanics, and just big things. So let's talk about just to remember, the correspondence principle says that in the limit of a large number of particles or a large volume, quantum mechanics should become classical mechanics. That's the correspondence principle, and thermodynamics is a part of classical mechanics. So, for example, let's say we had n particles in a box. So capital N is going to be our number of particles. These could be atoms, they could be molecules, whatever. They're in a box, so we just have the translational energy. We know what the eigenvalues are. CQ here stands for clicker question. Normally I would have a Socrative question if I were teaching this in the classroom. But I'll just let the cat out of the bag. The eigenvalues maybe look familiar. N squared, h squared over 8ma squared. What is the degeneracy? We never really talked about degeneracy when we were talking about the particle in a box, at least in a one-dimensional box, because there is no degeneracy. You just have the n, and just the energy goes up as n goes up. You would have degeneracy in a three-dimensional box because you could have an excited state in like the x, y, or z dimension, and that would be degenerate. Anyway, that's a sidetrack. Let's consider one particle, and the probability of being in state n depends on the Boltzmann distribution. That probability is proportional to e to the negative en over kt, or kbt. K is the Boltzmann constant, T is the temperature, and then this is the energy of state n. I say proportional. In fact, the proportionality constant is the sum over all of the possible states. So you can think of this as kind of a normalization constant. You're going to add together all the possibilities. That's your denominator, and then your numerator is basically the fraction that are in state n. So the probability of being in n is that fraction. Or we can call this e to the negative en over kt divided by q, where q is defined as that sum. Now, if we had degeneracies, this would look a little different. We'd need to account for those as coefficients in both the numerator and the denominator on each term. But anyway, so q is this normalization constant. It's also called the molecular partition function, and we'll talk more about that later. But if in the limit of a large box, we know that the energy levels get closer and closer together, so our sum becomes an integral. So the correspondence principle turns our sum into an integral, and then if you sum from 0 to infinity, you can plug that in, you can actually do the integral, and this is what you get. And this is sometimes called a over lambda, where lambda, capital lambda, is this funny thing. This ends up having units of length, which kind of makes sense, so that this is dimensionless. And this is called the thermal de Broglie wavelength. And basically, if the size of your system is quite a bit smaller than this thermal de Broglie wavelength, no, that's not quite right. If the size of your system is comparable to the thermal de Broglie wavelength, that's where you can do this correspondence principle, go from this sum to this integral. All right, so now in 3 dimensions, we'd have not just A, the length of the box, but we'd have A and B and C. And so, as you might expect, our Q would be equal to our QX, QY, QZ, and that would just be the product, because it would be the same integral in all 3 dimensions. And of course, A times B times C is the volume of the box. So we have volume over thermal de Broglie wavelength cubed. That's equal to Q. Now this was all for one particle in a box, one molecule. And like I said, Q is called the molecular partition function. That's what we call it in English. It's a sum over all the states. In German, it's called the Zustandssumme, which means sum over states. So that's, in a way, a better description. I don't know why we don't call it the sum over states. We call it the molecular partition function, which I think is a little inscrutable. But anyway, there it is. Okay, now what if we had two particles, so A and B? Then our total energy would be the energy of A and the energy of B. We define something called the canonical partition function, a capital Q, which is a double sum over all of the possibilities for the total energy of our system. Okay, so it's like the denominator, but now it's for the whole system. And if we break out all of the possibilities, they could both be in the ground state, or the first one could be in the ground state, first one could be in the first excited state, and so on. Lots of possibilities, ... right? All the way up to both of them being in the infinitieth state. You can sort these. So I could take, say, this E0 and this E1 and have all those, and then multiply by this E0 and this E1 and add all those and multiply the two together, because E times X plus Y is equal to E times X times E times Y. So you can think through how that works. So then, but then this is just the single molecule molecular partition function. So one for molecule 1, one for molecule 2. So that's just Q squared. So actually, I'm not going to prove this, but if we go, instead of being just 2 particles, if we go to n particles, instead of Q, capital Q being Q squared, it'll be Q lowercase q to the n. So the sum over all states for n molecules, this is at a fixed volume and temperature. Notice we're specifying the temperature. We also have the volume, our A times B times C. This is our capital Q. Our canonical partition function is equal to the molecular partition function to the number of particles. And that's if we have no degeneracies. If we had degeneracies, we'd have to put them in there, so that terms with multiple degeneracies get counted more than once. Q, by the way, is the holy grail of quantum mechanics. If we know the Q, or the lowercase q, because we can get the capital Q from the other, then all of thermodynamics can be calculated, as we will see. So if we know this sum over states, which we can get from the eigenvalues, then we're golden. So far we've only talked about capital E, which is the internal energy. Sometimes that's a capital U in Chem 317. What we also need now is entropy. We haven't talked about entropy at all in this class yet, but that's going to be another important contribution. So the entropy of a system, and this was Boltzmann's big contribution. Entropy of a system is equal to his constant, Boltzmann constant, times the natural log of W. What is W? W is the number of ways to arrange the system. So this is a pretty deep thing. And I know we often think of entropy as just like disorder, but it's much more concrete than that, actually. You have to think about the number of ways to arrange the system. Take the natural log of that, multiply by the Boltzmann's constant, and that's the entropy. Like, how does this make any sense? Well, let's think about it. For example, if we expand an ideal gas, we'd be increasing the volume. If we increase the volume, certainly we're increasing the number of ways we can arrange the system, right? Because there's more area for the gas particles to explore. And we know that we'd be increasing the entropy then, right? How about if we increase the energy of this system? Well, if we increase the energy, then some configurations that weren't accessible to the particles before will now be accessible. Like they can get too close or closer than they could before because they have that energy and they can rub up against each other closer before they reverse and spread out. So again, if we increase the energy, we'll be increasing the W and we'll be increasing the entropy of the system. Okay, so let's think about W for a very small system. Let's say we had n particles distributed over a certain number of states. So 4 particles, let's say. We'll call them A, B, C, and D. And they must be grouped with 3 of them in one bin, maybe the ground state, and 1 of them in another bin, maybe the first excited state. So most of them are in the ground state. How many different ways can this be done? And normally I'd have you figure this out if we were in class. So maybe pause the video and see if you can do it. But anyway, 3 in the ground state, 1 in the excited state. We could have A, B, C down and D up, or we could have A, B, D down and 1 of them up, or A, D, C and 1 of them up, or B, C, D and 1 of them up. Those are the 4 ways. There are only 4 ways. Now, in fact, we can figure this out using, what is this, probability, theory of probability. We could have W is equal to 4 factorial divided by 3 factorial times 1 factorial, because each time we can think of it as choices. So you've got, like, in the first spot, you've got 4 possible choices, and then once you've chosen A, then you have 3 choices, then you have 2 choices, then you have 1 choice, so 4 factorial. But because A, B, and C are the same, it doesn't matter what order we choose them in, so we have to divide by 3 factorial, and then 1 factorial. There's just 1 up there. In fact, the number of ways to arrange a system, if we generalize this to n particles, W is equal to n factorial divided by the number of particles in state 1 and in state 2 factorial, and yada, 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 through n, lowercase n. That's the number of particles that are in state J. We go 1 through n. Okay, that's our W, and we're going to use that when we come back to class on Wednesday. But just something to note here, as n increases, number of particles increases, definitely W will increase. And so the entropy will increase, and that fits with our intuition. More particles, there should be more ways to arrange a system, so the entropy should increase. What about energy? If the energy increases, then we could have more of the particles getting to excited states and even higher, right? You can imagine if the energy were so high, the particles could just go anywhere they wanted in excited states. So you'd have an even distribution across not just the ground state, but also the excited states. So then you'd have, instead of a big number times a bunch of 1s, you'd have a bunch of small numbers. And so then the denominator would be smaller in value because we're multiplying together a bunch of small numbers, and then the entropy would increase. So as the number of particles increases or the energy increases, the entropy increases. So entropy is an extensive property, we say. It goes with the size of the system, number of particles, and the energy. All right, that's it for today's class.